Hello everyone. Today let us discuss about Gauss law of electrostatics because Gauss law helps us to derive some expressions in the coming topics. So let us see what is Gauss law of electrostatics. So Gauss law mainly helps us to find the flux through a closed surface. Flux I have already explained in my previous video. Flux is nothing but the number of electric field lines passing through an area. So, to find the flux, Gauss law helps us in a simple way. Gauss law states that the total flux through an enclosed surface is equal to the total charge enclosed by the surface divided by epsilon naught. Once again, I repeat, the total flux enclosed by a surface is equal to the total charge enclosed by the surface divided by epsilon naught, where epsilon naught is the permittivity of the free space. Now, let us take one sphere and find the flux through the sphere and conclude the Gauss law. So, here there is a sphere which has a radius r. At the center of the sphere, we have a charge q. So the total charge enclosed by the sphere is q. To find the total flux through the sphere, first let us divide it into small area elements as shown in the above figure. You can clearly see in this figure, you can see there delta S is a small area element. One area element we have shown in the figure. Like that, the whole surface of the sphere we have to divide into small areas. Those are nothing but delta S. After dividing it into small areas, we have to calculate the flux through each area element delta S. As I have told you in my earlier video, the flux through a small area is equal to delta phi is equal to dot product of electric field and the area element. That is, delta phi is equal to E bar dot delta S bar. We all know the formula for the electric field. Electric field is equal to Q by 4 pi epsilon naught R square into R cap, where R cap is a unit vector along the direction of the distance. Here the distance to the area element is nothing but the radius. So once again I repeat, delta S is at a distance of R. R is the radius of the sphere because the charge Q is at the center of the sphere. Now R cap is a unit vector along the radius vector because radius is the distance for the area element from the charge Q. Now, coming to the point, we have to find the flux for the whole sphere. For that, first we have calculated the flux through a small area, that is delta phi is equal to E bar dot delta S bar, that is equal to Q by 4 pi epsilon naught R square into R cap into delta S bar. Delta S bar is nothing but area element whose direction we take along the normal. In this case of a sphere, the direction of the normal and the electric field both are in the same direction. You can clearly see that the direction of the electric field and the area element both are in the same direction. Therefore, we will take all such small areas and calculate the total flux. So we will take all such areas because every area is at the same distance from the charge Q, which is at the center of the sphere. Therefore, all area elements delta S bar are at the same distance from the center of the sphere. Therefore, let us calculate delta phi for a single area element is equal to q by 4 pi epsilon naught r square delta s. We all know r cap is a unit vector whose magnitude is 1. Now, to find the total flux, that is our main aim of this video. To find the total flux through the sphere, we can add all the flux through all the area elements. Therefore, total flux phi is equal to summation, that is, we use the sigma notation here, sigma all delta s q by 4 pi epsilon naught r square into delta s. To find the total flux, we are adding the flux through each and every small areas. And finally, all areas together will form the surface area of the sphere. Therefore, we get the total flux. Now, we have taken the total flux as adding up all the flux through all the different area elements. Phi is equal to sigma all delta s q by 4 pi epsilon naught r square into delta s. Now, we have every area element at the same distance. Therefore, adding up all such area elements will give us the total surface area of the sphere, which is equal to S. Therefore, phi is equal to q by 4 pi epsilon naught r square sigma all delta s, that is delta s. Sigma all delta s means adding up all small areas, that gives the total surface area S. Why we are adding like this? Because as I told you earlier, each and every delta S is at the same distance from the center of the sphere. Therefore, finally, we get the expression for phi. Phi is equal to q by 4 pi epsilon naught r square into S. Now, what is S? S is the total surface area of the sphere. We know the formula for the surface area of a sphere. S is equal to 4 pi r square. That is the standard formula that we will substitute here in place of S. Therefore, we will get phi is equal to q by 4 pi epsilon naught r square into 4 pi r square, because the surface area S is replaced by 4 pi r square. Now, in the numerator and denominator, 4 pi cancelled, r square can be cancelled. We will get phi is equal to q by epsilon naught. This is the expression for the flux through a closed surface. So, finally, we got the expression for the flux through a closed surface. Phi is equal to q by epsilon naught. This is called as the Gauss Law of Electrostatics. We can state it as electric flux through a closed surface S is equal to Q by epsilon naught, where Q is equal to total charge enclosed by S, where Q is equal to total charge enclosed by S. So finally, once again, we can say the Gauss law as the total flux through a closed surface is equal to the total charge enclosed by the surface divided by epsilon naught. This law helps us very much in the coming derivations. We have to derive three more derivations in this chapter. For that, for those calculations of the derivations and also for many numericals, Gauss law is very useful. In most of the numericals, we make use of this Gauss law. Thank you for watching this video. See you all in the next video. Until then, bye.